Now, let's look at the expected value of d squared. So if I were to do this problem, remember this is just x1 squared times the probability of x1 plus x2 squared times the probability of x2 plus, and so forth. That, again, is going to take us a lot of work to try to figure out, but we do know how to find, we have a formula for the variance. And I don't know if you guys remember, but I gave you a formula where the variance of x is equal to the expected value of x squared minus the expected value of x, that quantity squared. Notice that in here I have that e to the x squared. And if I were to solve this, I know how to find the variance. If I know it's a geometric distribution, there's a formula for me to find the variance. It's q over p squared. And I can find that. I already found the expected value of x in the previous slide. And so we know what that is. And I can go on and solve this for this value right here. So that's what we're going to do. First, we're going to find the variance of d. Variance of d is q over p squared. Q is 0.2. P squared is 0.8 squared. And that gives us 0.3125. So now my equation becomes, if I solve this equation for this value right here, the expected value of d squared, I have to add this value to both sides of the equation. Our outcome by solving this equation for the expected value of d squared, like I said, we're going to add the expected value of d, the quantity squared, to both sides. And we end up getting the expected value of d squared is equal to the variance of d plus the expected value of d, that quantity squared. We found that the expected value of d is 0.3125. We found that on the previous slide here. And we found that the expected value of d is 1/4 or 0.25. We're going to square that. So the expected value of d squared is equal to 0.375. Now, sometimes when you have a geometric random variable, instead of your random variable being described as the number of failures, it may be described as the number of total number of trials until the first success. So there are two ways that a geometric distribution problem can be worded. The random variable could be the number of failures before the first success, or the number of trials until the first success. Even though it sounds similar, these are different random variables. Because when you talk about the number of trials until the first success, you are including that last trial in your count. So in this case, y would be x, where x represents the number of failures, just as described before the first success, plus the one success that you have. Another way to look at it is if you want to write it in terms of x, you can certainly go on and write x is equal to y minus 1. What would the probability function be in this case? It would be, in this case, the probability function of y is going to be y, the probability that y is equal to k, is the probability that x is equal to k minus 1, okay, just using this formula here. And so what happens is p is still going to be there's only going to be one P because there's still only one success. But this time there are K minus 1 failures because I'm including that last trial as a part of my random variable. So if I have, for example, if I flip a coin 6 times and on that 6th trial I get a success of heads, then how many successes do I have? I have 1 success and I have 5, which would be 6 minus 1 failures. And because your probability distribution changes here, your mean and your variance will also change. And so the mean becomes 1 over P if you're including all of the trials in your random variable. And the variance is going to be, instead of Q, well, actually the variance doesn't change in this case. It's going to be Q over P squared still. So what changes is the mean and the probability function. So let's look at an example here. A fair die is rolled until a 2 shows on top. Let Y be the number of trials until the first 2. So in this case, getting a success would be getting a 2. A failure is not getting 2. They want us to find the probability that Y is between 2 and 4, including 4, but not including 4. 2, rather. And they want us to find the mean of Y. We know that the probability of a success of rolling a 2 in this case is going to be 1 over 6, right? Well, what is the probability that the random variable is between 2 and 4? Now, remember, this is the number of trials until the first 2. So our random variable Y represents all of the trials, including the last one. Whereas when we're dealing with the number of failures, the random variable only represented up until the last trial. What are the numbers, or the number of trials between 2 and 4, not including 2? Well, that would be either 3 or 4. And since the probability of success is 1 over 6, we know that the probability of failure is 5 over 6. 1 minus 1/6, which gives us 5/6. Here, I know that there's still 1 success, but there are 2 failures. So in this case, the powers have to total your random variable. And when Y is equal to 4, we're going to have 1 success, but we're going to have 3 failures. Again, in this case, if we're looking at the total number of trials as your random variable, then this sum, these two numbers have to sum to whatever your value there is. That gives us 0.2112 if you convert it to a decimal.